The ocean has been quietly waiting for 10 kilometers below the surface since before humans existed. Picture a single water droplet. Now picture 10 million of them pressed together into a column so deep it swallows the tallest mountain on Earth and still reaches further down. And somewhere at the bottom of all that weight, life is moving. Most people who are afraid of the ocean are afraid of the wrong thing. They picture teeth, fin shapes slicing through the surface, the sharp, sudden arrival of something fast. But the ocean's deepest power has nothing to do with creatures or speed or attack. It has nothing to do with what lives inside it. The ocean's greatest force is the one thing it has always had in extraordinary abundance, and that is simply weight. Water is heavy. That fact sounds obvious when you say it this way, but most of us never live inside it. We float on the surface of the ocean or stand at the edge of it, looking out, and we see something that seems almost passive, something that catches light and moves in long, slow rhythms and carries ships without complaint. We do not feel the weight of water because we are above it. We skim across its surface the way a dragonfly skims across a pond, touching it lightly, taking none of it on. But the moment you go beneath that surface, the relationship changes entirely. At 1 meter down, the water pressing on your body from every direction is already something you can feel. Not dramatically, not painfully, but it is there, like a hand laid gently on your shoulder. At 10 meters, that feeling has grown into something more insistent. At 30 meters, recreational divers begin to understand for the first time that the ocean is not neutral territory. It is not indifferent to their presence. At that depth, the water is already pushing against them with twice the force of the atmosphere they left behind on the surface. And below 30 meters, the numbers begin to do something quietly alarming. The ocean does not need to attack you. It does not need to chase you, or find you, or decide to harm you. It only needs you to go deep enough. Because at depth, the water is simply doing what water has always done, following gravity, pressing against everything, filling every available space with its mass. The ocean does not need teeth. It has something more patient than teeth. It has physics, and physics does not hurry, and physics does not miss. It begins long before you can see the darkness coming, before the light fades, before the color drains from the world around you, before you reach the depth where things become strange and unfamiliar. The pressure has already begun to make itself known. This is the part that surprises people who have never dived before. They expect the darkness to arrive first, as if pressure and depth and the loss of light are all the same thing arriving together. But they are not. Pressure is the first visitor. A scuba diver descending from the surface begins to feel it almost immediately in the ears. This is the most familiar sensation associated with pressure change. That muffled, full feeling, the slight ache that builds if you descend too quickly without equalizing. It is the same sensation you get when an airplane changes altitude, when an elevator drops too fast in a tall building, when you drive over a mountain pass. The pressure of the air or water around you is shifting, and the air trapped inside your body is not keeping up. Divers learn to equalize constantly as they descend, gently forcing air into the middle ear to match the surrounding pressure. It becomes routine after a while, almost automatic, something the body learns to manage without much thought. But that routine task is itself a reminder of something important. The body is already in negotiation with the ocean at a depth of just a few meters, already working, already compensating, already acknowledging that the environment is applying a force that the body must actively manage. This is where pressure lives in everyday human experience, close to the surface, familiar, manageable. The first few meters of the ocean are territory we can visit and return from without special equipment, without unusual risk, without much thought. Children feel it in swimming pools. Snorkelers feel it on shallow reefs. It is gentle here, almost companionable. But pressure does not stay gentle. It follows a rule, and the rule does not make exceptions. At sea level, before you enter the water at all, the weight of the Earth's atmosphere is pressing down on you with a force scientists call 1 atmosphere, or approximately 101,000 pascals of pressure. You have lived your entire life inside this pressure. You were born into it and have never known anything else, which is precisely why you do not feel it. The human body is exquisitely calibrated to exist at 1 atmosphere, to the point that the pressure is simply invisible to us, part of the background of existing rather than a sensation we can identify. The moment you descend 10 meters into the ocean, something fundamental shifts. The column of water above you adds another full atmosphere of pressure to the one already pressing down from the air. You are now at 2 atmospheres. The water at this depth is pressing against you with twice the force you have spent your entire life in. The effect is not catastrophic here. Divers operate comfortably at 2 atmospheres, but the number is important, because the rule does not stop at 10 meters. At 20 meters, you are at 3 atmospheres. At 30 meters, 4. At 100 meters, a depth that requires serious technical training, specialized equipment, and careful planning, the pressure has reached 11 atmospheres. The weight pressing on every square centimeter of your body at 100 meters is 11 times the weight of the entire atmosphere you breathe on the surface. At 1,000 meters, where the last recreational submarine expeditions reach, and where only specialized research vehicles dare to go, the pressure is over 100 atmospheres, more than 100 times the force of the entire atmosphere pressing inward from every direction at once. At 6,000 meters, the threshold of the deep ocean trenches, the places where the seafloor has been swallowed by the Earth into crevices so deep they feel like wounds in the planet, the pressure exceeds 600 atmospheres. At the very bottom of the Mariana Trench, at nearly 11,000 meters, the pressure approaches 1,100 atmospheres, 1,100 times the weight of the sky, pressing against every surface in every direction simultaneously. These numbers do not get easier to absorb, no matter how many times you read them. That is not a failure of imagination. It is an accurate response to a reality that has no parallel in everyday human experience. When people imagine what pressure would do to the human body, they often imagine something dramatic and sudden, a body simply crushed, like a can squeezed in a fist. But the reality is more specific than that, and in some ways more interesting, because the human body is not entirely vulnerable to pressure in the same way a hollow object is. The reason for this lies in our composition. The human body is approximately 60% water, and water is almost entirely incompressible. It cannot be squeezed into a smaller space regardless of the pressure applied to it. This means that the majority of the tissue in the human body, muscle, fat, blood, the fluid in our cells, would survive extreme pressure intact, because the pressure outside would simply be matched by the pressure within. A jellyfish can survive at the bottom of the Mariana Trench for this very reason. Its body is almost entirely water, with no internal spaces, and so the crushing pressure outside is simply transmitted throughout without distortion. The vulnerability of the human body to pressure is located precisely in the spaces where we are not water, the places where we carry air. These are the lungs, which are essentially 2 large air-filled sacs sitting inside the chest. The middle ears, which are small air-filled chambers behind the eardrums. The sinuses, a network of air-filled cavities in the skull behind the face. And the gastrointestinal tract, which at any given moment contains a variable amount of gas. It is into these air spaces that pressure becomes dangerous. As external pressure increases, it compresses the air in these cavities. The lungs, which at sea level hold several liters of air comfortably, would be compressed progressively as depth increases. A breath held at the surface and carried to 10 meters would find its air compressed to roughly half the volume. At 30 meters, the same breath would occupy approximately a quarter of the space. At 100 meters, A breath taken at the surface would be compressed to less than a tenth of its original size. The lungs, at that point, would be folded inward against each other inside the chest, pressed by the surrounding tissue and fluid, and a human being in that situation, without the specialized equipment that provides pressurized breathing gas at ambient pressure, would be in immediate danger. This is why scuba equipment works the way it does. It does not simply provide air. It provides air at exactly the pressure of the surrounding water, so that the body's air spaces can stay expanded and functional no matter the depth. Without that matching pressure, the air spaces lose. They always lose. Because the ocean has more patience than lungs. Imagine descending without equipment. Not as a warning or a horror scenario, just as a thought experiment. A slow tracing of the sequence. The ears would be the first to register the change. Within just a few meters, the pressure differential across the eardrums would build to the point of pain. The drums are thin membranes stretched across a small space, and they are sensitive to even small pressure changes. Without equalization, without the ability to force air into the middle ear to match the surrounding pressure, the eardrums would be under stress almost immediately. Below a certain depth without intervention, they would rupture. It is not a gentle failure. It is abrupt and painful. But the depth at which this happens without equalization is surprisingly shallow, well within the range of a swimming pool. The lungs would follow a more gradual curve. A trained breath-hold diver can descend to impressive depths by taking a large breath at the surface and allowing the chest to compress naturally. The human chest is more flexible than it appears, and the lungs can be compressed substantially before serious injury occurs. But there is a limit, and below that limit, the lung tissue itself begins to fail. Blood is forced into the lung cavity to compensate for the volume loss, a phenomenon called blood shifting that occurs naturally in practiced divers. But this compensation has boundaries. Sinuses would add their own complaints along the way. The small openings that connect the sinus cavities to the nasal passages can become blocked by swelling or congestion, and a blocked sinus under pressure is acutely painful, like something pressing outward from inside the skull. Equipment introduces its own hierarchy of failure points. A diving mask traps a pocket of air against the face, and if the diver fails to exhale gently through the nose to equalize that pocket, the mask can create a powerful suction effect as the surrounding pressure rises, a condition called mask squeeze, where the soft tissue of the face is pulled toward the lens of the mask. Standard compressed air cylinders have their own limits tied to the behavior of gases under pressure. Oxygen becomes toxic at depth. Nitrogen causes narcosis, a peculiar intoxication that begins around 40 meters and deepens unpredictably. Submarine pressure hulls are engineered to tolerances that seem impossibly precise given what they must withstand. Even a single flaw in the geometry of the hull, a weld that is slightly irregular, a join that is not perfectly circular, creates a stress concentration, a point where the forces are not distributed evenly across the metal. At sufficient depth, that point can become the place where everything ends. The light begins to fail long before you expect it. At the surface, in clear, open water, sunlight is immediate and generous. It scatters through the first few meters in long, shifting columns, illuminating everything in a pale blue-green glow that moves and ripples with the surface above. Colors are vivid here. Reds and oranges exist. The world looks the way it does in photographs, bright, alive, full of detail, but light is absorbed by water at different rates depending on its wavelength. Red light, the long end of the visible spectrum, is absorbed first, disappearing within the first 10 meters. It is a quiet loss. Things that are red begin to appear brown, then gray, then simply dark, even though there is still plenty of light around them. Divers who cut themselves at depth are sometimes surprised to find that their blood does not look red. It looks green. The red wavelengths needed to make blood appear red no longer exist at that depth. They were claimed by the water column above. Orange follows red, disappearing before 20 meters. Yellow fades between 20 and 30. Green lingers longest, persisting down to around 70 or 80 meters in very clear water. Blue is the most penetrating wavelength, the one that survives the longest descent, which is why deep water in photographs appears the color it does, that particular shade of blue that feels both beautiful and remote. By 200 meters, even blue light has been mostly absorbed. The zone between about 200 and 1,000 meters is called the mesopelagic zone, or the twilight zone, a name that suits it because there is still a faint light here, but it is so dim that it is barely perceptible to the human eye. This is not the full darkness of the deep ocean. It is something stranger than darkness. It is light that has been traveled so far and been absorbed so much that it has been reduced to a blue-gray suggestion, a hint of sky seen from the bottom of a very deep, very still lake. Below 1,000 meters, the last traces of sunlight are gone entirely. Whatever light exists in this world from this depth downward is generated by the creatures living in it. Consider what it means to have a column of water above you that is 1,000 meters tall. At sea level, the atmosphere above you extends roughly 100 kilometers into the sky and exerts about 10 tons of force per square meter on the surface of the Earth. That number is large enough to be meaningless in human terms, which is why we do not feel it. The body is used to it. It is the baseline, the background, the normal. Now add to that baseline a column of seawater 1,000 meters high. Seawater weighs approximately 1,025 kilograms per cubic meter, which means a column of it 1 meter square and 1,000 meters tall contains over 1 million kilograms of water. That is the weight pressing against every square meter of surface at 1,000 meters depth, stacked on top of the atmospheric pressure already present at the surface. It is the approximate mass of a fully loaded Boeing 747, pressing on every square meter of your body from every direction simultaneously. At 3,000 meters, roughly the average depth of the world's oceans, that weight triples. The pressure at the average ocean floor is enough to collapse any airspace, any hollow structure, any cavity that is not either filled with liquid or reinforced to an extreme degree. At 6,000 meters, we enter territory where comparisons begin to feel strained, because there are few things in everyday life massive enough to serve as reference points. The pressure at 6,000 meters is roughly equivalent to having 60 cars placed on your thumbnail, pressing down through an area smaller than a postage stamp, across your entire body, simultaneously. At the bottom of the Mariana Trench, the comparison shifts to something more like the weight of a small elephant balanced on each coin-sized area of your skin. The number is not meant to be horrifying, it is simply accurate. The deep ocean floor exists under conditions that are genuinely alien to everything about the way human life is structured. A submarine is not a naturally buoyant object, and it is not designed to fight pressure by being stronger than the ocean. The ocean is always stronger. The design philosophy of a submarine pressure hull is not dominance, but distribution, a carefully calculated way of spreading force so that no single point bears more than its engineered share. The most critical element of this is the shape. A perfect sphere distributes pressure equally across its entire surface, which is why the deep-sea submersibles that reach extreme depths, vehicles like the Trieste, or the modern limiting factor that explored the hadal zone, use spherical personnel capsules. There are no corners, no edges, no transitions where forces concentrate. The pressure arrives at the hull from every direction and finds no single point weaker than any other. It is the geometric solution to the problem of the ocean. Larger submarines, designed for military or research use at depths of several hundred meters, use a cylindrical hull rather than a sphere, a cylinder capped at both ends with curved sections. The choice of cylinder is driven partly by the need to create useful interior space, but the cylinder must be as geometrically precise as engineering can make it, because any deviation from a true circle creates inequalities in how pressure is distributed. Oval is not an option. Slightly flattened is not acceptable. The hull must be round. The materials must be able to withstand not just the initial application of pressure, but repeated cycling, the expansion and contraction that happens as the submarine ascends and descends. Metal fatigues. Welds develop microscopic cracks after enough cycles. This is why submarines have depth ratings that are not simply physical limits, but engineering recommendations based on the calculated lifespan of the hull under repeated use. And then there is the implosion risk. This is the failure mode that defines the deep ocean, the one that is quick and absolute and leaves very little behind. An explosion moves outward. It is the rapid expansion of gas or force from a central point, a release of energy that pushes everything away from its origin. We have an intuitive understanding of explosions because we live in an atmosphere where pressure and force naturally propagate outward. An explosion is, in some sense, the same kind of thing as the forces we experience every day, but amplified to a destructive degree. An implosion is the opposite. It is the inward collapse of a structure when the pressure outside it exceeds the pressure inside. In the deep ocean, if a sealed air-filled cavity, a submarine, a pressure vessel, a research sphere, develops a structural failure at extreme depth, the event that follows is not an explosion. The ocean does not push outward. The ocean collapses inward. The mechanics of an implosion at great depth involve the surrounding water closing in on the failing structure at extraordinary speed. The outer shell fails at one point, and that failure propagates around the hull in milliseconds, the metal and composite material folding inward as the water fills the space. The implosion creates a pressure wave that travels through the water and can be detected by hydrophones, underwater microphones, at distances of thousands of kilometers. When researchers are looking for a lost submarine or vessel at depth, they often look first for this signature, a single, sharp impulse in the acoustic record, a sound that travels very fast and very far through the deep ocean. The implosion itself lasts a fraction of a second. The air inside the failing structure is compressed with such violence, in such a short time, that it generates an enormous spike in temperature. In the milliseconds of the collapse, the temperature inside the imploding space may briefly exceed that of the surface of the sun before the water completes its inward rush and fills the space entirely. It is a very quiet event from the outside. From the ocean surface above, there is no explosion, no fireball, no visible sign. The water is disturbed slightly, and then it settles, and the deep ocean resumes its silence, as if nothing happened at all. And then, in the middle of all this, there is something alive. It is strange to arrive at this point after everything that came before, the collapsing air spaces, the pressure equivalent of skyscrapers, the implosions in the dark, and find that the ocean does not agree with the picture we have built. Because while all of those forces are real and accurate and overwhelming, they are not the whole story of the deep ocean. They are only the story as seen from the surface, by organisms built for the surface, imagining what the depth means in surface terms. The deep ocean is not empty. It is not silent. It is not a place where life was squeezed out millions of years ago and left nothing behind. It is one of the most biologically diverse environments on Earth, populated by organisms that have spent hundreds of millions of years solving every problem we have just spent several chapters establishing as near impossible. They live in the crushing dark. They live without sunlight. They live in the cold, at pressures that would reduce any of our technology to debris. And they do not simply survive there. They thrive. They have evolved coloration and bioluminescence, and feeding strategies, and reproductive systems entirely calibrated to a world we cannot easily visit, and have barely begun to understand. Life did not fail to colonize the deep ocean. Life went there first. We are the newcomers, trying to build machines strong enough to follow. The reason deep-sea creatures do not implode is the same reason jellyfish can survive at any depth without special equipment. They have eliminated the vulnerability. they do not carry air pockets. The body plan of a deep-sea fish, crustacean, or soft-bodied invertebrate is built around a fundamental structural principle: near-total incompressibility. Their tissues are composed of fluids and semi-solid materials that transmit pressure rather than resisting it. The pressure outside the body is matched, almost perfectly, by the pressure within. There is no sealed airspace where forces can concentrate. There is no cavity the ocean can reach into and squeeze. The body simply accepts the pressure from all directions and holds its shape because it is the same substance, under the same conditions, as the water surrounding it. Deep-sea fish have evolved specific adaptations that go beyond the mere absence of air bladders. Their cell membranes incorporate different proportions of unsaturated fats than surface-dwelling fish, which keeps the membranes fluid and flexible rather than rigid at low temperatures. Their proteins are structured to maintain their function at extreme pressure rather than the denaturing, the unfolding, the breaking down that happens when you apply those pressures to proteins evolved for the surface. The enzymes in their bodies have shapes that work at 1,000 atmospheres. This is not an accident or an exception. It is the product of evolutionary time, of generations of creatures whose proteins worked slightly better at depth and who survived slightly better as a result, selecting over hundreds of millions of years for biochemistry suited to the deep. Some creatures, like the deep-sea amphipods that have been found in the Mariana Trench at depths exceeding 10 kilometers, appear almost shrimp-like when viewed in photographs. Familiar in outline, curved bodies, appendages, small, dark eyes. They look as though they belong to the same general category of things as the shrimp on a dinner plate, and in evolutionary terms, they are not entirely wrong. But their internal chemistry is as different from their shallow water relatives as a high-altitude plant is from its lowland equivalent. The shape is similar. The world it is built for is alien. At 1,000 meters, the sun has not existed for a long time. Below this depth lies the zone that scientists call the mesopelagic, or, more evocatively, the midnight zone. And the name is accurate in the sense that matters most. There is no light here that comes from outside. The photons that left the surface have been absorbed by a kilometer of water. The only light in the midnight zone is the light that living things make themselves. Bioluminescence is so common in the deep ocean that it may be more unusual for a deep-sea creature not to produce light than to produce it. Estimates suggest that as many as 70 to 90% of organisms living in the deep ocean are bioluminescent. Anglerfish carry a small lantern ahead of their jaws to draw prey. Dinoflagellates, single-celled organisms that form the base of many marine food chains, glow when disturbed. Certain species of squid flash and pulse in complex patterns. Deep-sea jellyfish trail luminous curtains as they drift. The darkness of the midnight zone is, in this sense, something other than pure darkness. It is a darkness populated by small, moving lights, a kind of cold, slow fireworks display that has been running for millions of years with no audience other than the creatures producing it. The temperature at this depth is typically between 2 and 4 degrees Celsius. Not quite freezing, but close. The cold slows metabolic processes, reduces the need for food, allows some deep-sea creatures to survive on remarkably sparse nutrition. The midnight zone is not lush. Food is scarce here. What arrives from above is mostly the slow rain of dead organic matter, pieces of dead plankton, fecal material, decaying fragments of larger organisms that scientists call marine snow. It falls constantly, gently, from the sunlit waters above toward the floor far below. And creatures in the midnight zone are adapted to make use of almost every particle of it. This is an ecosystem built on patience and darkness, and the slow falling of things from a brighter world above. Below 6,000 meters, the ocean has a different name for its deepest spaces, the hadal zone. From Hades, the ancient Greek realm of the dead, refers to the ocean's trenches, the narrow, elongated chasms that form where tectonic plates collide, and one edge is pushed down beneath the other. These trenches are not distributed evenly across the ocean floor. They appear in specific places where the geology of the seafloor has folded into its deepest expressions, and they extend to depths that, even after all the numbers already explored in this script, still seem improbable. The Mariana Trench in the western Pacific Ocean is the deepest of these. Its lowest point, the Challenger Deep, was first measured in 1875 and has been remeasured several times since with increasingly precise technology. The current accepted depth is approximately 10,935 meters below sea level, close enough to 11 kilometers that the number 11 becomes the most useful approximation. 11 kilometers. Deeper than any mountain is tall, deeper than the cruising altitude of a commercial aircraft. The pressure at the bottom of the Challenger Deep is approximately 1,100 times atmospheric pressure at sea level. The temperature sits just above freezing. The darkness is absolute, and has been absolute for longer than multicellular life has existed on the surface. And yet, when cameras have been lowered to the floor of the Mariana Trench, first in 1960, when the bathyscaphe Trieste carried 2 men to the bottom in a descent that took nearly 5 hours, and many times since with unmanned vehicles, they have found life. Microbial life exists in the sediment in enormous concentrations. Small crustaceans called amphipods have been found in large numbers. The hadal snailfish, a pale, translucent fish that resembles something between a tadpole and a ghost, has been photographed swimming near the bottom. Life has found a way into even this, the most extreme of the ocean's environments, and has made something viable there. The hadal zone covers only about 0.5% of the total area of the ocean floor. But in terms of extreme environments on Earth, it may have no equal. There is a point at which the numbers stop being comprehensible and start being simply enormous. 11,000 meters, 1,100 atmospheres. At this depth, the pressure on any surface is equivalent to roughly 1,100 kilograms pressing on every square centimeter. That is slightly more than a metric ton of force applied to a surface the size of a thumbnail. Distributed across a human body, the total force would be something in the range of hundreds of thousands of metric tons. A number so large, it ceases to communicate anything meaningful to the human intuition. The only way to operate at this depth is to eliminate the problem of airspaces entirely, or to engineer a structure so precisely that the pressure is distributed without any single point of failure. The Trieste, which reached the Challenger Deep in 1960, used a spherical pressure hull made of steel approximately 13 centimeters thick. The sphere was small, barely large enough for 2 people to sit inside without touching, and it was surrounded by a large structure filled with aviation gasoline rather than air, because gasoline, being nearly incompressible, would not be crushed at depth and could provide the buoyancy needed to return to the surface without requiring air bladders. The windows of deep-sea submersibles are among the most carefully engineered components of the vehicles. They cannot be perfectly flat glass. A flat surface cannot distribute pressure evenly, and so they are typically thick cones of specialized acrylic material that taper inward, a shape that allows the pressure to seat the window more firmly in its mount, rather than pushing it inward. The deeper the pressure, the more tightly the window is held in place. This elegant inversion, using the crushing force of the deep ocean to hold the window in, rather than fighting that force, is characteristic of how deep-sea engineering thinks about the problem. You do not fight the ocean at this depth. You redirect what it does into something that serves you. At 11,000 meters, even these solutions feel provisional. Every material behaves slightly differently at extreme pressure. Metal flows, given enough force. Polymers compress. Lubricants behave unexpectedly. Cables and connectors and electronic components all exist in a world so far from the conditions they were tested in at the surface that every dive to this depth is a negotiation with the unknown. a careful trust extended to engineering that cannot be fully verified until it is asked to perform. The deepest part of the ocean is not a wasteland. The floor of the Mariana Trench, seen in footage from cameras lowered on long cables from research ships, looks at first like a kind of pale desert, a flat expanse of soft sediment the color of pale clay, undisturbed, unmarked, stretching in all directions until the lights of the camera fall short and the darkness returns. It looks empty. It looks like the end of the world. But the sediment is alive. In a teaspoon of sediment taken from the hadal floor, there are millions of microorganisms. Bacteria and archaea, the ancient, simple life forms that predate every complex organism on Earth, are densely packed into the first few centimeters of the ocean floor sediment, metabolizing organic matter that has drifted down from above over millions of years, cycling nutrients and gases in a slow, cold biochemistry that has been running continuously since long before the first fish appeared in the fossil record. The deep ocean floor is, by the standards of biology, one of the most densely populated microbial environments on Earth. Above the sediment, amphipods move in groups. These small crustaceans, which resemble elongated shrimp and range in size from a few millimeters to more than 30 centimeters in the deepest trenches, are scavengers and opportunists. When a piece of food reaches the floor, a dead whale, a large fish, any substantial organic mass, the amphipods can detect it from surprising distances and arrive in numbers, consuming it with an efficiency that returns its nutrients to the ecosystem quickly. The hadal snailfish, the deepest living vertebrate currently known, moves through this world with an unsettling ease. It is not built for the look of a predator. It is pale, almost translucent, with soft gelatinous tissue and no rigid bones that could be compromised by pressure. It has no swim bladder. Its tissue is saturated with a compound called trimethylamine oxide, which stabilizes its proteins under extreme pressure in the same way that the proteins of other deep-sea creatures are stabilized. It swims slowly. It feeds on the amphipods. It is, by every measure, at home. The ocean floor is not the end of life. It is a different beginning of it. The entire floor of the world's oceans covers an area of approximately 361 million square kilometers. Of that total surface, a surface larger than all the land on Earth combined, spread across every ocean basin on the planet. The area that has been directly observed by any form of human technology is estimated at less than 25%. Some estimates place it much lower. We have mapped more of the surface of Mars than we have mapped the floor of the Pacific Ocean. We have better resolution images of the Moon's terrain than of the deepest ocean ridges on Earth. The machines we have built for space observation, the telescopes, the orbiters, the rovers, have given us detailed portraits of worlds hundreds of millions of kilometers away. The tools we have for the deep ocean are comparatively crude, comparatively few, and comparatively seldom used. This is not an accident. The deep ocean presents engineering challenges that are, in some ways, more complex than the challenges of space. In space, the primary problem is the vacuum, the absence of pressure, the absence of atmosphere. Engineers solve this by building structures that maintain pressure within and exclude the vacuum without. The ocean inverts this problem with a force that is, in practical terms, far more difficult to manage. The crushing inward pressure of the deep ocean acts on every surface simultaneously, from every direction, with a magnitude that increases with every additional meter of depth. A spacecraft in low Earth orbit is under no meaningful external pressure. A vehicle at 11,000 meters is under more than 1,000 times the pressure of the atmosphere. There are, at the time of this writing, only a handful of vehicles in the world capable of reaching the full depth of the Mariana Trench. The number of humans who have descended to the deepest point of the ocean, the Challenger Deep, is smaller than the number who have walked on the surface of the Moon. The deep ocean remains, in this very real sense, the least explored and least understood environment on Earth. It is a world that covers most of our planet and has been shaping its chemistry and climate for billions of years. And it is a world that most of us will never see, will never be able to visit, and will only encounter in the translated form of footage sent up through kilometers of cable, processed by machines, and displayed on a screen in a room with air pressure and temperature calibrated for the surface of the Earth. There is something in this fact that is difficult to articulate but easy to feel. The deep ocean is not distant in the way that other planets are distant. It is beneath us. It is the floor of the world we live on, the underside of the surface we navigate every day, and it is almost entirely unknown. Not because we have not tried to understand it, but because the conditions that make it what it is also make it extraordinarily difficult to reach. The ocean is patient. It has been down there for a very long time. It will be there when all of this is over. The research vessels and the submersibles and the hydrophone arrays and the pressure-rated cameras sending their footage upward through the dark. The water will still be pressing with the same weight against the same floor, in the same cold, in the same darkness, and the same creatures will be moving through it, indifferent to the thin layer of light and air and attention that the surface has briefly paid. Close your eyes. There is a world 10 kilometers beneath the place where you are lying right now. Not a metaphor, not a poetic image. A real world, with real creatures living in real cold darkness under real and extraordinary pressure, doing what they have always done. And it is very, very quiet down there.